Okay, this is Chapter 5, Physics, College Level Physics 1, and this is a continuation of Work and Energy, Chapter 5, Module 3, Part 4. This is the last part for the chapter. So we're going to talk about spring energy and what a spring basically does, how it measures up in physics, and how we can solve things like the potential energy of a spring and other types of problems. Okay, so I'll give you some background first. The force of a spring is equal to kx, okay? And this is known as Hooke's law. And we see that k is actually equal to a ratio between the force and between the distance the spring is stretched. Force versus distance. The slope is the spring constant. So if we look at a graph, force versus distance, we have the graph showing the force increasing over the distance, okay, and k is the slope of this graph here. Also, work done, or the energy done, is basically the area under this curve. So we need to calculate, if we want to know what the energy is, by taking Hooke's law, F equals kx, we just need to derive an equation for the energy. And we can do this by using integration and calculus. Okay, so the work done is going to be equal to this is going to be our problem that we're going to solve. And when we do, we get this equation right here. So this is our energy equation for springs, specifically potential energy. So in a conservative system, the work done in a spring is equal to the potential energy of a spring. So let's look at some spring dynamics. We can also measure energy in a spring with a mass attached to it. Let's first eliminate PE for gravity, because as we show you the equations, we have to get rid of the gravity, where K is the spring constant in Newton meters. Okay, so this is basically all these terms right here. If they are set to 0, then we have a conservative system, okay? And so we just basically put the final conditions in under these brackets minus the initial conditions here. And we can take the potential energy for gravity and we can make it go to 0. So we just have these two terms, the first one and the spring for each in each of the brackets. Okay, so at equilibrium, okay, so at equilibrium, this is when the spring is not stretched, and we are going to call this x equals 0. We don't know the velocity. Of course, the velocity could be 0 if the spring is not moving with the mass. So let's take a look at the equations, and we're going to come up with an equation to figure out the velocity after we pull the spring out a certain distance and let go. What is the velocity when x is equal to 0? This is at the equilibrium point. Derive an equation for v final because v initial will be 0. So this is our equations right here that we're interested in. We're going to take, first of all, we have v final and we have x final. We have v initial. Now we know that the initial, we're not going to need that because the initial is 0. And the same thing over here, the final, this term will go to 0 too. So we have this equation and this equation that we're going to equate to each other. And then we're going to solve for the velocity of f. And we don't have friction, so mu will be equal to 0. So we have a diagram here now. We have our spring potential energy equation. Spring constant units are newtons per meter. They're basically the stiffness of the spring. Higher the constant, the larger the constant, the stiffer the spring. So at x equals 0 is at this position, equilibrium. And then if we put a load or pull the spring out with the mass on it and just leave it there, we have potential energy and we have a load, a force that's acting on it, will be acting on it. So let's look at a problem. What is the potential energy of a spring when it's stretched out? X equals 0.125 meters. The spring constant is 200 newtons, okay? So we can disregard the negative in our answer since energy has no direction. So in this part right here, so it's at equilibrium, and then under load, it's pulled out to 0.125 meters. And when I talk about this negative, I'm talking about this right here. We can disregard that for now. And we can plug in the numbers and we get a potential energy of the spring when it's pulled out 0.125 of 1.56 joules. So let's look at a problem. Find the velocity of the object as it passes through 0. That's x equals 0. That's the initial condition. This is the final condition. So these are all the equations that we would want to have at our disposal so that we can take and choose what we will apply to this problem. Okay, we have kinetic energy initial plus potential energy initial for the spring. We have kinetic energy final, and we have potential energy final for the spring again. So we know that kinetic energy initial, we don't need that. Okay, potential energy initial, we do. Kinetic energy final, yes, that's going to give us our velocity. And then we have our potential energy final, that's just going to be 0. So the equations we're going to need this one, and we're going to need this one, okay? So here we have the mass pulled back with the displacement, and we're just going to let go of it, and then we're going to need to find the velocity when that that mass crosses the x equals 0 line. Okay, so again, we have these two equations. The ones in yellow are the ones we need, and then we're going to take them, equate those together, and we're going to solve for V of f. Okay, here's V of f right there. So if we equate this to this and then solve for V of f, we get a velocity as the mass passes through the equilibrium point of 0.791 meters per second. Let's look at non-conservative energy. This is where we have the kinetic energy, the change in kinetic energy, plus the change in potential energy does not equal 0. It's going to be equal to some type of non-conservative type of energy, usually caused by friction in these cases. Okay, so non-conservative energy or force is caused by friction between the block and the surface as it's sliding along. So this is our frictional force equation. Mu equals mg. As you know, mg is the normal force. And then if we just take the normal force and mu and take that times the amount of distance the spring is pulled out, then we have the work, the non-conservative work done, or the potential energy of the spring, or kinetic energy of the spring with friction. So let's move on to this equation here, and this is the equation that we get. I'll go through this. First of all, this right here is the work, the non-conservative work done right here, caused by the friction. We have the kinetic energy, which is going to be valid because it has a final, and then we have the initial potential energy, because it's going to be pulled out and it's not going to be released. It's stored energy. And so all we need is these three terms, and we need to solve for V of F. So solving for V of F gives us this expression right here. And we just plug in our values and we find we get 0.367 meters per second. So be careful when you're doing the algebra to figure this out with the minus signs. But this is what you should be getting as far as the equation for this type of problem. So let's do an in-class exercise. We have a mu of 0.35. We have a mass of 25 kilograms, and we also have x is going to be equal to 1.5 meters. So we're going to pull this out 1.5 meters. Okay, so find the velocity at x equals 0 in a conservative system. Find the velocity at x equals 0 in a non-conservative system with friction. Okay, so we're going to do with no friction and with friction in a conservative system. The potential energy is equal to the kinetic energy. And so let's just plug in the values and we get 450 joules. Now we can solve. It's conservative. We're going to use the conservative equation right here. Solve for V of F, and we get 6 meters. The frictional force now, we can calculate the frictional force. We know what mu is, we know the mass. Acceleration of gravity is 85.8 newtons. So velocity with friction. Okay, so let's take a look at that. So our frictional force is 85.8. This is going to be our equation that we're going to use, and we just plug everything in, and we get 5.07 meters per second. Okay, thank you. That is the end of our discussion for Chapter 5.